All right. Hi, folks. This is Larry Mussolino. I wanted to help out with the Module 7 discussion. A few students were confused, I think, a little bit on this one. So why don't we talk about this for a second? And first thing it says here is look over this help on integrals and review the example about indefinite integrals. So let's take a minute and talk about integration or integrals. Now, integrals, let me open up a blank sheet here. Let me just start up Word so I can get a blank sheet. All right. So let me give you a little background. So let's use a function, a simple function. Let's take x to the third. Well, you can find what's called the derivative function. We label it as f prime. And you remember there's a rule for this. We call this the power rule. And what you did is you took this exponent, brought it down in front as a multiplier, and then copied the x down, subtracted 1 from the original exponent. So the new exponent is x to the 2 here. So this was the derivative function. And if you remember, the derivative function gives you the slope of the tangent line to a function. Okay? Well, what we want to talk about now is something called the antiderivative. And antiderivative and integration mean the same thing. There's two ways of saying the same thing. What is an antiderivative? Well, an antiderivative would take this derivative function and get you back to the original function. That's why they call it antiderivative. It's kind of undoing the derivative function. And we use a symbol that looks like this, integration like that. And if you wanted to integrate 3x squared, and then we put a dx out here, dx means we're using x as the variable of integration. Well, there's a rule for this. The rule says if you want to take the integral of x to an exponent, you add 1 to the exponent and divide by the expression n plus 1. You might notice this kind of looks the opposite of derivatives. When you were taking the derivative of a function, you subtracted 1. But now you're taking the antiderivative, it's adding 1. So it kind of makes sense that it's undoing the derivative function. So let's work it out. Well, what you do now is you say, oh, this number 3 is a constant. I could just copy it down. So I'm going to take this x to the 2 and apply this rule. Well, this says add 1 to the exponent. So I'm going to write 2 plus 1 and divide by that same expression, 2 plus 1. So this is going to work out to be 3 x to the 3 over 3. The constants 3 cancel out, leaving me just x to the 3. So when I take the antiderivative of 3x squared, it is getting me back to the original function, f of x. Now, one way you can check this is if you come up with an integral answer, right? We came up with x to the third. If I take the derivative of this answer, I should get back to 3x squared. And of course I do. But when you take an integral like this, you could have an arbitrary constant out here. So I'm going to put a plus c. Because if this worked out to be x to the third plus 7.2, I just made up 7.2 as an example. But if I took the derivative of this function, I would still get back to 3x squared. Because you remember the derivative of a constant like 7.2 is 0. So we use this arbitrary constant plus c there to take into account the possibility that this original function could have had a constant out there. Okay. So if you notice what we're doing here is we're taking the integral of f prime of x dx. Right? This 3x squared was the derivative function. Well, when you do this, integration and derivatives kind of cancel each other out. They're inverse operations, they're opposites. So that would get you back to f of x. All right, so that's the background, and that's what they're asking you to do in the discussion board. Let me go back to the discussion board and let's read the instructions. And let me also get Desmos maybe side by side so we can, let me put this here. And let me get Desmos here side by side. All right, let's do that. Let me get this over here. Okay, so let's read this again. And I'm going to use this as an example, this Desmos graph. All right, here it is. It says, look over the background information on integrals. And like the example we just did, if the original function was x squared, so let's say the original function was x squared, you wanted to take the integral of this, sometimes we call it capital F of x, the integral of x squared. Remember, the rule is add 1 to the exponent and divide by that same new exponent 3. And then you usually add an arbitrary constant out here. All right, so it says graph the first derivative from your problem in discussion 6. Let me do a simple example. Let me graph x to the third just to give a little sense of what you're going to do. All right, I also want to graph the derivative function. So for that, all I have to do is type into Desmos g prime. And Desmos will automatically graph the derivative. Of course, it's 3x squared, so you could type that in, but we could just let Desmos graph g prime. Let me activate that graph. And so the red is the original function. The blue is the derivative. All right. Now it says, using the integral notation, graph the antiderivative. Here's the way you can do that. What you can do is you can say capital G of x is the integral from 0 to x of the derivative function. And I'm going to put this arbitrary constant out here, plus d. All right. So now if I graph that function, let me activate that graph. Let me get rid of some of this stuff. Let me activate that graph. If you notice, the green graph, which is the antiderivative, is the same as the original function, which is the red, but it's been shifted up. Now, I created the slider down here for d. Let me make d be 0. If d is 0, where is 0? There is 0. If d is 0, then the green and the red graphs are sitting on top of each other. Let me make d a little different than 0 so you could see it. Can you see how the green graph now is essentially the same as the red graph, but vertically shifted up a little bit according to d? Let me make d be 5. Well, if I make d 5, notice the green graph now has been shifted up. Got to get d to be 5. Oops, can't get the slider. There it is. So do you notice this red graph has been shifted up by 5 to get me the green graph? So what this is showing is if you take the integral of the derivative, it gets you back to the original function. And again, the reason is integration and derivatives are opposites. They cancel each other out. It's kind of like saying antiderivative of a derivative gets you back to the original function. Okay? All right, here's another question. What is the y-intercept of the antiderivative function? Well, if you notice here, the y-intercept is 5, and that corresponds to the value of d, this constant. And of course, you can modify d. All I have to do is change the slider, and it'll shift the y-intercept up or down according to the value of this constant d. Okay? And again, you might say, what's the point of this constant? Well, the constant is trying to take into account that the original function, if y was x to the 3 versus y equals x to the 3 plus 9, let's say, when you take the derivative of either one of these functions, you get the same answer. Because when you take the derivative of a constant, you get 0. So when you're taking an antiderivative, you might not know what the constant was in the original function, if any. And so usually what we do is we include this arbitrary constant. Usually we call it a c, but you can call it anything you want. Let me do a more complicated example. So let me go and grab, let me clear some of this stuff here. Let me go and grab, let me turn these off. And let me grab one of the examples from the week 6 discussion. Here it is. And, in the week 6 discussion, they were asking to try to think of some application where this might be useful. Now, what you can also do here is if you want, you can put in curly braces x greater than 0 to limit the value of x. So, for example, if x is representing time, maybe you just want to show the values of x greater than 0. If x represents the number of units you're manufacturing on a production line, again, x can't be negative, so you might want to limit it to be positive values only. All right, so maybe I want to come up with some kind of an example for this function. Well, let me think of something here. Maybe this is let's say the concentration of a drug. So this y-axis might be the concentration of a drug in your bloodstream versus time. Let's say the x-axis is time. So what might happen is you take the drug initially, the concentration goes up, but then it reaches a maximum and the concentration slowly falls back down. Okay, so let me go ahead and plot the derivative function. Let me clear that off here. All right, let me plot the derivative function. So for that, all I have to do is write f prime of x. So here is the derivative function in black. But the instructions also said plot the antiderivative. So I'm going to use this red function here. Notice it says capital F of x is the integral from 0 to x of the derivative function. And if you notice here, and I put plus c as an arbitrary constant, and Desmos will put in the slider for you. And notice how the red and blue graphs are identical except for a vertical shift. And again, what this is showing you is if you take the integral of the derivative function, it gets you back to the original function. Another way to say it is I'm taking the antiderivative of the derivative. Let me show that to you here in the symbol so you could see it. This symbol is the antiderivative. This symbol is the derivative. But again, if you take the antiderivative of the derivative, those operations cancel each other out, and you get back to the original function f of x. All right, and one of the instructions said, make the maximum of the antiderivative twice as great as the maximum value of your function. All right, well, the maximum value of my function here is about, what is that? 4.5, I'm going to guess, something like that. So I want the blue curve to have a maximum of about 9. Well, all I have to do for that is take the slider for C and modify it. Let me do that. I'm going to take the slider for C and make C get bigger and bigger. And let me drag the graph down so you can see it. And all I have to do is get C to go up to about 9, roughly. And there it is. The maximum of the red graph is about twice the maximum of the blue graph. What about the y-intercept of the red graph? So remember, this red graph is the antiderivative function. What about the y-intercept? Well, if you notice right here, the y-intercept is about 8.6, and that's the value of the constant. Okay, so I hope this helps. Use this notation in Desmos for easy graphing. Enter the original function. You're getting this from the week 6 discussion. So this is given to you. Then just type in f prime of x. That will graph the derivative function. And then type in this notation. This will get you the antiderivative function. And you might say, well, where do you get this fancy integration symbol from? Let me show you that. Get rid of all these. All you have to do is type in the word integral. So let me add something here. I'll just show you. So let's say you wanted to add in a capital G of x equals integral. Well, I'm going to start typing in the word INTE, and Desmos automatically figures out that you wanted to type integral, so it puts that symbol there for you. So all you have to do is start typing INT, and Desmos will generate that symbol for you. Okay? And then I would just put here 0 as the lower bound, x as the upper bound, and then I could put, here G prime of u du plus a constant. I'll use the constant a. And notice it says, do you want to add a slider? Say yes. And now you have a slider that you can modify. All right, let me know if you have any questions. Hope this is helpful on your Module 7 discussion board.